thanks for giving me the opportunity to talk about this. So when we want to do NMR experiments, we always have the problem of poor nuclear spin polarization. So if you look at the polarization of a nuclear spin at 9.4 Tesla roughly, then it's very small. And if we compare this at a similar magnetic field to electron spins, it's yeah, the difference is quite clear, and we can see that the polarization of the electron spin is a bit higher. And in dynamic nuclear polarization experiments, we usually transfer or try to transfer electron polarization, electron spin polarization to nuclear spins to enhance their signals. And the way we do that in liquids is at room temperature, we take a polarizing agent that can be a small organic radical. We put them together with our target molecules. And then we can actually look a bit inside what happens. Now you see in red the electron spins and blue nuclear spins. They are more depicted not to their actual size, but rather to their magnetic moment or magnetization rather. And you can see that they tumble and flow and they move all the way and they come close to one another. So they will have interactions. And these interactions, this interaction, which is called hyperfine interaction, can be or is modulated by molecular motions. For instance, we can have modulated hyperfine interactions of dipolar or of contact or Fermi-contact nature. And these motions can then induce polarization transfer via cross-relaxation, and the result is a hyperpolarized nuclear spins. And what do we actually have to do to be able to use this hyperpolarization? To induce it, we have to irradiate with microwave and then subsequently detect the NMR signal with after the irradiation. And the good thing about this is we can actually repeat this experiment as many times as we want. So signal averaging is in that way not really an issue. So to explain this a bit more in with a bit more physical meaning, we can look at a 4-level diagram of an electron spin coupled to a nuclear spin, and we can actually derive the Overhauser equation if we assume a steady state condition where we constantly irradiate this EPR transition here. And the hyperpolarization will then be induced by cross-relaxation, so by W2 and W0 rates. And if we do that, we can end up with our Overhauser equation, where we have the signal enhancement. The signal enhancement can be positive or negative. The sign in the end is not too important. Then we have the coupling factor, which is a descriptor of the cross-relaxation and contains the information of how is the polarization transferred. So what is the underlying mechanism on this polarization transfer? Then we have the leakage that gives us information of how much of the overall nuclear relaxation is channeled through the paramagnetic ingredients, so the radicals, for instance. And last but not least, we have the saturation factor, which determines how well do we actually saturate this EPR transition here. And now we can look at all the different parameters, and I would like to start with the enhancement. And the enhancement can be measured if you measure an NMR spectrum with and without microwave and comparable temperatures, and then you compare the integrals. But so the experiment is rather straightforward. So I would like to look at a couple of different examples with you to show you what has already been done, and at what magnetic field what works, what nucleus best. This list now is by no means extensive. It's simply a collection of examples. And we have here, for instance, DMP on protons at 0.3 Tesla. So it's X band for EPR. So that's why it's a very common magnetic field. And we have, for instance, on water is an enhancement of roughly 170. And also for toluene, you can get enhancements above 100. Not only protons has been measured at X-band, but also carbon has been studied extensively. Actually, there is this huge table by the Dawn group who use a flow setup to actually determine all the enhancements and measure the signals. And they, throughout the years, they collected a lot of data. And also, for instance, the group from Sonjihan in Santa Barbara measured some results at 13C nuclei, which are depicted here. They also measured 1H, but yeah, I chose now here the 13C. And if we now go on to a bit higher magnetic field, we can look at 3.4 Tesla, which is W band in EPR terms. We can see that for ethanol, we can also get an enhancement still of a factor of 14 roughly. This was from the group in NAMEG and by, I think by Arno Kentkens. And so we can also measure fluorine, 19 fluorine. And the interesting part about the fluorine is that actually the signal enhancement remains rather constant. If we go from X band to W band, it doesn't really matter too much. We still have an enhancement of roughly 20. And then we have also already a bit of an older study from the Griffin group, who measured various nuclei at 5 Tesla, and they obtained sizable enhancements for different nuclei, such as 15N, 31 phosphorus, and also 13C actually. And yeah, so if we now go to even higher magnetic field, we can still measure proton DMP in water, which was done by the Priesner group, and they obtained a factor of 80. Yeah, also we did some work on 13C. We found a factor of 1,000 roughly at 3.4 Tesla, and a factor of 400 at 9 Tesla. And last but not least, the group from Tallahassee with Thierry Dubroca, they measured a phosphorus enhancement and obtained an enhancement even at 14 Tesla, which is the highest on this list, of a factor of 160 approximately. So there's quite a few data points already in the literature, and people have been working on different nuclei, and I think it's really a interesting approach to also look at different nuclei and see how they actually work at a high field. And now we can look at the next parameter, which would be the saturation factor. And it basically defines how well is the EPR transition saturated. And for a one-line radical, which we can define BDPA in liquids at the high enough concentration, the saturation factor is rather easy to obtain because we can derive it directly from the Bloch equations. However, if we now go to a radical that is used abundantly in DMP measurements in liquids, we find that nitroxides at least have a two-line system. If we have 15N labeled nitroxides, if it's 14N, we have even 3 lines in the EPR spectrum due to the hyperfine coupling. And if we can only irradiate with one given frequency, that would result in an expected saturation factor of only 1/2, because we can only irradiate on this position. However, the two lines actually interact with one another through a Heisenberg exchange, but also through nuclear relaxation in certain systems. And through that, we can actually achieve much larger saturation factors than only 0.5. And experimentally, we can also measure that. If we have an EPR spectrometer, we can perform a so-called Eldor experiment where we have one frequency, the detection frequency, set on one position. So for instance, on this S1 line here, which corresponds to the low field line in the EPR spectrum. And then we take an Eldor pulse. So it's simply a long microwave pulse of the order of, let's say, 3 to 5 microseconds. And we sweep it through the EPR spectrum. And what we see is once we are on resonance with the first line, we will see an almost complete depletion of the signal intensity, which is a result of the long pulse, and we saturated the line completely. Then we will recover some of our signal, and then once we are on resonance with the second line, we again see a drop in intensity, and this drop is then caused from the crosstalk of these between the two lines. So we can eventually achieve a saturation of, here in this case, 0.78, can be even much higher, can be up to 0.9, 0.95. So this is one way to measure the saturation if we have EPR pulse capabilities. However, if we want to do that at high magnetic fields, these capabilities are very scarce. It's very, and if we want to even do DMP with it, it's yeah, I'm not sure if there's a setup that can do that. So what we can do, or what the Priesner group actually did, was they measured the saturation factor at 9 Tesla through the paramagnetic shift suppression. So how this works is if you induce or introduce a paramagnetic substance into a liquid, you will change the chemical shift of the nuclei which are in this solution. And if you now apply resonant microwaves on resonance with the paramagnetic substance, you will partially recover this shift because you sort of quench the paramagnetic substance. And in order to do that, you first need to subtract the temperature contribution of the microwave to the sample. This can be done through measuring the temperature from an internal standard. Here in this case, it was water and glycol, I think, ethylene glycol. They compared the chemical shift difference and calibrated so the temperature. Then they added the paramagnetic substance and were able to then measure the NMR line shift as a function of the microwave power, end up with measuring the saturation factor, which is a cool way, I guess, to do that at high field. So the next parameter, so the third one of the Overhauser equation, is the leakage factor, and it depends on the T1N relaxations with and without paramagnetic substance. So how much of our overall relaxation appears or happens through the paramagnetic substance? And well, it's rather easy to measure. You just measure the T1N values. Here's just an example of toluene, for instance. And if the difference of these is not large enough, so the leakage factor is small, that would destroy or reduce significantly your signal enhancement. And to circumvent that, we can actually increase the polarizing agent concentration, and that should increase the leakage factor then. Okay, so now we come to the coupling factor, which actually contains all the information about the polarization transfer mechanism. And we can write it in terms of rates, where we have here the cross relaxation rates. But we can also write it as, which was derived from Solomon, with the spectral densities. And if we just put these expressions in, we end up with this term here for the coupling factor, where we have dipolar and a contact, so Fermi contact contribution. So what are these spectral densities? What causes them? And for this, we have for dipolar coupling, there are two molecular motions that can induce dipolar cross relaxation, which are rotational diffusion and translational diffusion. And then we have for the contact part, we have the scalar coupling, which is usually modulated by molecular collisions. So these three molecular motions can these three motions can modulate our hyperfine coupling on different time scales. And we can now describe those time scales for each of the motion. And we can start with the rotational diffusion. And usually the spectral density is described by a Lorentzian for the rotation. And yeah, this here you see on the right, you see that I plotted it as a function of the magnetic field for tau c with roughly with 30 picoseconds. And if we now go to the next one, which is the translational diffusion, we actually usually employ the force-free hard sphere model, and which was introduced by the Fried group, and they derived such a spectral density. Rather long expression, and but the important parameter here is the correlation time, which is defined as the distance of closest approach over the local diffusion coefficient. And so we can actually use this to obtain distances of closest approach, and this has been used, for instance, from the group in Santa Barbara to actually gain information about the hydration. Water hydration of, for instance, some proteins, I think, already a while back. What we can also do is we can now take this spectral density and compare it to the rotational one. And what we see is that it's the decrease is a bit less steep. So however, yeah, the general pathway is similar. And now the last interaction, which is the scalar coupling, can be described by this spectral density, which follows the pulse model, which was developed by Müller-Warmuth and his co-workers. And usually we have a train of pulses that are separated or occur with a frequency tau p, have a hyperfine isotropic hyperfine interaction of the size a, and a duration of 2 times this tau. This is depicted here. You have these different pulses, and then at a time interval of tau p, and with the duration of tau 1 or tau 2. And the pulses have a Lorentzian shape, and we can now also use this and this correlation spectral density and plot them on top of the other two, and you see that the behavior is yeah, like it is here, and it's not super different from the others. So now we defined basically the way our different motions can modulate our hyperfine coupling and therefore induce cross relaxation. So change the coupling factor. And we can also express now this term in terms of these relaxivities. And if we do that, we end up with this, which is quite a bit longer, but it actually distinguishes now between all the different motions. And if we now ask the question, what can we actually do with it? Well, we can find out if this works at high magnetic fields, for instance. Can we have a coupling factor that is large at any given magnetic field? And for this, we need to know on what time scales actually these molecular motions operate. And this is usually so this is now for small organic radicals. Yeah, for solid molecules, it can go down to as small as 20 picoseconds. However, the Fermi contact the molecular collisions can be very short, so they can be in the range of sub-picoseconds. And now we can plot the spectral densities again, but with a bit more realistic values for the tau. And what we can see here immediately is that the contact interaction is the one that survives the longest towards high magnetic fields. Okay, so now we have the framework, and we can now also calculate the coupling factor. And what you can see here on the left is the coupling factor as a function of the magnetic field with tau, so the rotation equals 20 picoseconds, and which is the same for the contact. And you can see here on this picture that you can only obtain a coupling factor from non-zero at magnetic fields which are of interest, which I would say larger than 9 Tesla, if we have almost only scalar cross-relax, a scalar coupling contributing to the coupling factor. However, now this picture is it's a bit problematic because I already showed you that the tau con can be much shorter than this. So we can actually use the same equation and plot it a bit differently. And if we do that, so what you see here now is we used a diffusion of 25 picoseconds. We skip this time the rotation, and we plot different contact contribution. You can actually see that for rather short contact times, which are not unrealistic, we can still observe sizable coupling factors at magnetic fields higher than 10 Tesla, for instance. And as the coupling factor basically defines the overall DMP efficiency, if all other parameters are optimized, that is a rather promising prospect to actually see DMP at high magnetic fields, if the scalar mechanism is the dominant one. The dipolar, unfortunately, appears to be decaying rather fast. Okay, I would stop here, and if there are questions, we could discuss them.
So far, it seems you don't have any question, but I have one question here. What determines this time constant for the Fermi contact interaction? And you talked about a pulse there. I didn't really understand, what do you mean by pulse? Is it the contact period?
Yes. So you can have molecular collisions, which are basically modulating the scalar interaction. And then this tau con is, maybe I should have be more specific, is then this part here in the exponent. So it's basically half of the duration of this of one of the molecular collisions. So each of these pulses defines a molecular collision, and then these collisions can be defined by a duration, and the duration is then this tau con, which I plotted here.
Okay, so is it possible to regulate this by changing the viscosity of the medium?
That's a good question. What you can definitely do with the viscosity is to change the translational diffusion, because you have the diffusion coefficients in it. If you change the viscosity of the medium, I'm not sure if you then change the tau, the duration of the collision. It could be, because then if it's a lower viscosity, then it stays longer in the vicinity. It could be. I have no information if there has been a study about it, so I cannot say for sure.
So just to visualize this factor a bit more, so suppose I have a BDPA molecule compared to a tempo molecule. BDPA is large. So when you talk about these molecules colliding, can it contact anywhere on the BDPA surface? Or say if you have a radical which is bigger, larger surface area compared to a tempo, will it be better in terms of this constant factor to have a larger molecule?
I actually talk about that very point in the second part. If it's okay for you, I would postpone the answer, because I will definitely touch this topic, and will explain it.
Sure.
There's also one. Let me see.
Yeah, there is one question. So the question is, can you comment on the overall range of solution conditions that are accessible at high magnetic fields? And in general, what's the general microwave heating effect for polar solvent?
it is large. So you heat your sample. If you don't work in a microwave cavity, you heat the sample a lot if you use polar solvents. I will also talk about this in a couple of minutes, a bit more in detail. But generally speaking, at high magnetic fields, it's a trade-off between using a microwave cavity, which restricts you in terms of volume, or using a non-resonant setup where you can lose larger volumes, but then you have more severe heating effects.
Mm-hmm. And are you going to show us a diagram of how the cavity looks like? It might help some of us.
Of a microwave cavity, no?
Yeah, like where do you put your sample and the sample holder?
Yes, there will be one example of it.
Okay, I think we can proceed for now and take other questions later.
All right. Hello.
So Marcel, I think we can proceed for now.
Yeah, my presentation was stuck. Okay, so part 2. Yeah. So now we basically start where I stopped a couple of minutes ago, and now we have this nice picture, but we would like to know, can we actually show this experimentally? And in order to do this, we have to choose the right target at high magnetic fields, because we want to do DMP at high field, because only then we have resolution. So we can do it at low field, there it works perfectly fine. But if we actually want to use it in high resolution NMR, we need high magnetic fields. And for this purpose, we need a nucleus that displays a scalar dominant cross relaxation, so that where the coupling factor is dominated by scalar relaxation. And unfortunately, protons don't do that. They are almost exclusively displaying dipolar dominated coupling factors, which leads to a positive, I should have mentioned that, positive coupling factor. On the other hand, 13C does the opposite. Most of the moieties are actually scalar dominated, and we can obtain negative coupling factors for it. So we chose 13C, and we measured the signal enhancement, saturation, leakage, and obtained then the coupling factor at various magnetic fields. And just to comment on the line width, this was a study to demonstrate that DMP actually works, and it was not these measurements were performed at very low volume in EPR magnets and capillaries, so the line shape was not really possible to optimize. So that's why they look a bit broad. But if we now then get the coupling factors from these measurements together with some measurements from the literature and put them on our graph, which you already seen, we can actually use then this very equation to reproduce these data when we use a contact contribution of 0.5 picoseconds and then a diffusion. We don't need to introduce the rotation at this point, so we end up with a I would say nice fit for the experimental conditions we have. We can then also do this for chloroform, where we need 2 of these contact times, one which is responsible for the high efficiency at low field that decays rather early, and then a second one that survives longer, which is also 0.5 picoseconds and is responsible for the efficiency at high magnetic fields. So this tells us it works at high magnetic fields. So we can also measure it, and we did this in a collaboration with Frankfurt. The group of Professor Priesner and Vasil Denisenkov helped us or performed the experiments with us, and we were able to actually measure these at 9.4 Tesla and went up to even 600 for this tetrabromo compound, but not only for those, also for other stuff, so like pyruvate or diethyl malonate. We can obtain decent and signal enhancements, and we can even resolve all the splittings here. So it's kind of working well also on other compounds, on non-halogenated compounds. So you asked for a picture. I can only give you, unfortunately, I don't have one of our own here today, but this one is the setup which was used in Frankfurt to do the DMP experiments at 9.4 Tesla, which is where they use where they irradiate the microwave from this side and through the RF coil, which is called, so this setup is usually in the literature of their papers, they refer to it as the helical setup. So what are other people doing on this? So there is another study from Frankfurt and also one from Tallahassee again. And the people from Frankfurt, this was very recent. So it's actually, I think the paper is out for 2 weeks, where they use now a new resonator, a Fabry-Perot resonator, where they put the sample on as a thin film, and in that setup they were able to measure signal enhancements in water with not too much heating. I think I'm not completely sure, but I think the heating is not so much of an issue in that resonance setup, because they can separate H and E field. And what you can see here, they obtain significant enhancements for different biological compounds with a maximum of this imidazole of about 50. They use roughly 100 nanoliters for this because it's still a microwave cavity, or resonance structure, I should say. And here, on the other hand, Thierry Dubroca again, they measured at their high feed DMP liquid state DMP setup. They measured also here 13C enhancements, and I chose here the example of phenylacetylene, where they obtained an enhancement of roughly 35. They also measured chloroform and tetrachloromethane. For chloroform, they got, I think, around 70. So just chose this one because it's something else than chloroform, and this is to demonstrate that it works on a variety of different moieties actually. So now if we compare these two setups, actually it is rather striking. What is still a limitation is, if we have a nice resonance structure, we are restricted in our volume to roughly 100 nanoliters, and in the end, the resolution is also limited simply because of the arrangement. However, if we choose not to use a resonance setup, so no microwave cavity, we get extensive heating. So we get microwave absorption by the solvent, and we heat up our sample significantly up to the point where we cannot measure anymore. We also work on this. We have here, this is a picture of our setup. It's our lab. We have gyrotron now and a 400 megahertz magnet, and I hope soon I can show you something. But for now it's not there yet. What can we do actually are there other ways other than optimizing the hardware to increase our DMP efficiency? Well, we can tweak a bit the physics, right? So we can particularly consider again the contact interaction, and here the duration, again the duration of the interaction, the frequency of these interactions, and the hyperfine interaction, and to understand what molecular structural parameters actually influence those. We looked at different polarizing agents, and you see here now BDPA and different nitroxide derivatives. And what we did, we went to 1.2 Tesla, and measured all the Overhauser parameter and measured then obtained then the coupling factor. And you can see this here, and we did this for our chloroform and CCl4. And what you can see is that there is a trend. So there is some kind of dependency on that. And just to be sure that this was also that it is really coming from the contact interaction, contact contribution, we measured also the 1H part. Here you can see this, and the trend is not visible, not the same trend is visible in the coupling factor of the protons. So we were quite sure that is coming from the scalar part. And so as a first step, we compared spectral electron spin densities, and we did that for Tempone and for BDPA, for instance. We also have, for the other nitroxides, they look similar. And what you can see is that the spectral electron spin density is highly localized for nitroxides, whereas it is for BDPA, it's spread all over the place. However, with a maximum here on this allele group, I think it's 20–25%. However, the BDPA performs rather poorly. So we think that for an efficient polarization transfer, you need these, you need the spin density to be localized on one position, and then you have these, you have as much polarization transferred as possible during one of these molecular collisions. We went then on and also calculated the solvent accessible surface, which was also done by the group from Linden Emsley rather recently, to investigate some solid state DMP. And we did this now for a comparison of all these radicals, particularly here the BDPA versus a nitroxide, and you can see, the solvent accessible surface is defined by taking a spherical probe and rolling it over the van der Waals radius of the DFT optimized structure, in this case for the different molecules, for instance here Tempone and BDPA. And from that we can then get the accessible surface of each of these moieties. So they are color coded here, and orange is then the highest accessibility. And what you can see is that the oxygen of this and of the nitroxide is highly accessible. Whereas if we compare this to the BDPA, we see that the position of highest spin density is actually quite buried. So apparently not only the spin density has to be accessible, it also needs to be localized, or vice versa. And if we do this now for all the radicals, we see that the correlation is rather good. And what we think is that this accessibility actually has an influence on the frequency of the encounters, because it could be that what it should do is that the larger the accessibility, the larger the likelihood of a given encounter. So the larger the probability that they collide in a way that is actually favorable for polarization transfer. And this should influence, or should be resembled in the frequency of encounters, therefore in this tau p. And interestingly, this part, so the tau p, is not dependent on the frequency. So it should be a parameter that is independent on the frequency and help us in terms of DMP efficiency. So large accessibility appears to be desirable for efficient DMP in liquids. This of course goes for the radical moiety, but also for the nucleus of interest on the target molecule. If it's completely buried within the molecule, the DMP enhancement can be expected to be lower. So what you can see here is that the correlation is, I think, not too bad. However, for the highest point for this FN2A, which we call our fullerene nitroxide here, it doesn't really doesn't really follow this trend. So we looked into this a bit more in detail, particularly because we measured it at low and high magnetic field. And while it is performing exquisitely well at 1.2 Tesla, at 9.4, there's almost nothing left. And this is all the more puzzling if you compare it to nitroxides, which are not that large, so they are small. Here we get an enhancement of 500 at 1.2, but only 400 and still 400 at 9.4 Tesla. So that was a bit puzzling to us. Why is that? And in order to find out why we have it like this, we performed an MD study. So we put both once the small nitroxide and then the large nitroxide into a bath of chloroform and looked at if we can identify molecular motion, structural reorientations that could have an impact on this. And for Tempone, we can identify if we use the descriptor of these two methyl groups. So what you see here on the right is the CC distance of these two methyl groups plotted as a function of the time evolution of the MD run. And you can see here relatively clearly that we have two stable chair conformations which interchange via a twist conformation, and this is nicely resembled by the CC distance description. And if we now compare this to fullerene nitroxide, we take the same descriptor, and here on the right you see the trace with the zoom. We see no interchange between chair 1 and chair 2. Now the chair interchange, so this should not be what causes the large signal enhancement, because this is we can see it here is a long time scale. But what we can see here for the fullerene nitroxide, if we use the same descriptor, is that there is a difference between structure A and structure B. And this corresponds to a opening and closing, if you will, of these two methyl groups. So they come a bit closer to one another and then they go away again. And this could be, so this closing could be a movement towards a transition-like state to go into this chair and into a twist or chair conformation. However, this is not possible in the fullerene nitroxide structure because the backbone is here linked via this ring to the fullerene. So they go a bit together and then they go away from one another. And you can see this here in the CC distance changing from A to B. And actually this opening and closing is modulated on the time scale of 3 to 6 picoseconds. And that's exactly the time scale which we need to explain the good performance at low magnetic field and the bad performance at high magnetic field. So we think that this local structural reorientations can actually also play a crucial role in DMP in the liquid state. And with this, I have a brief summary. I think I showed you that DMP at high field, it can work. It works. We have demonstration for that. Polarizing agents in general, the molecular structure of our DMP system is of crucial importance and can be optimized if we retain high accessibility, high localization of the spin density, and we also have to take care of local structural reorientation. So if we want to design an optimized polarizing agent, and then we can finally also still, and this is also necessary, improve the hardware, which is already good, but we need to go further to actually make DMP really better at high fields in liquids. And with this, I would like to acknowledge all the people from our group, and particularly the people who are highlighted, who work with me on the on the project, different projects, and yeah, and thanks for the organizers to actually giving me the opportunity to present here.
Yeah, that's great. So we have a couple of questions for you, Marcel. The first one is by Elia Koprov. His question is, could the difference between polarine and non-polarine radical mostly be in the electron relaxation rate? And he says, like, the bigger the molecule means faster electron relaxation. Did you measure relaxation on these systems or the saturation factor?
Yes, we measured the relaxation. Yeah, so the electron relaxation rate of the fullerenes is not so easy to measure actually. At low field it still works. At high field it's a bit troublesome. Wait, could the difference between? So the rotational contribution to the coupling factor, which is now which you can describe by the Lorentzian spectral density, is not the factor that makes the coupling factor at low magnetic field good and at high magnetic field bad. That is, we tried that. We actually we did that, and if you well.
I have allowed Ilya to talk in case he wants to.
Okay, perfect. So basically this is the rotational contribution, and you can see that so it is decreasing the coupling factor. This is not for protons, but it still does. And for scalar it doesn't help. For if it actually influences the electrons spin relaxation, so that would influence the saturation factor. And
yes, that's right.
And
that's what I was thinking about.
Yeah, so it does definitely affect the saturation factor. At low magnetic field, the saturation factor for fullerenes is much higher because actually the nuclear relaxation of the nitrogen kicks in and helps with the transfer. So it's much better at X-band for saturating. However, if you go to higher magnetic fields and even at 1.2 Tesla already, the saturation factor is not so good anymore because the lines of the fullerenes are rather broad, and then you cannot saturate anymore with the microwave pulse or with the microwave frequency.
I see. This is fascinating stuff. This is really beautiful, these systems.
Yeah, the fullerenes in general are really cool. That's true. Okay. I hope I could answer this.
I have an add-on. I think it may not be possible on gyrotron-based setup, but is it possible to do some kind of modulation and have a better saturating factor for this kind of system, if that's the limiting case?
At high field, or
yeah, can we have like a modulating B0 modulation coil and then have a better saturation?
You can have a bit of saturation. Otherwise, there would be no signal enhancement of here at 9.4 Tesla. So a tiny bit, of course. More than that, I don't know.
Okay, so we have another question from Walt Masevsky. And his question is, so if your hypothesis about fullerene is correct, can you tune its polarization performance by changing temperature of the sample?
Because then this would enhance this opening and closing. Could be. We never did a temperature dependent study on this, I have to admit. But this would be worth trying to see. In theory, if that motion is responsible for the change in the impede performance I showed you, then you should also be able to change that with the temperature. Yes. And if at different temperature these movements are different in time scale, then yes. But there is no, yeah, we did not do the measurement, so I cannot give a definite answer to that.
So we do not have any other questions from the participants, but I have a general concern. So you talked about the accessibility of the radical and the target molecule, they should collide. And for real practical purposes, we want to enhance a bulkier, a more like relevant molecule, maybe a protein molecule, where this problem would be even more severe. So what's your take on achieving Overhauser DNP for a bigger molecule like proteins?
So for proteins, for instance, so if your nitroxide, for instance, if you continue to use nitroxides for the DNP, then your collision time is not necessarily dependent on both, or other way around. The collision time and the translational motions are dependent on both molecules, right? On the protein, but also on the radical. And if your radical is small enough, your molecular collisions can still be fast enough to get signal enhancements at molecules that are as big as proteins. I think I'm quite sure of that, because the interaction time should not change too much. You will still have this fast modulated sub-picosecond time scales, which was yeah, it's a pity I couldn't show it. It is there will be a new publication from Thomas where he actually shows this, that there is even if you have for instance a transient complex for protons or something like that, for a hydrogen bonding sort of interaction, you can still have underlying that, you can have sub-picosecond modulation of your hyperfine coupling. So that for this, and for the second part, for the accessibility, of course there will be problems when you want to hyperpolarize the core of the protein. That I think I agree, but still you can easily reach the outside and then use correlation spectroscopy to get your signals further. And also you can use experiments where you if you want to look at the interaction of a protein with, let's say, a drug or a small activator or whatever, you can hyperpolarize that small molecule and then look at the interaction between that and the protein.
Yeah. And we still don't have any other question, but I have my last final question. So you talked about Overhauser with microwave saturation. So there are some recent work by Chris Vokes from England, where he talks about first hyperpolarizing electron using some light activation, say fullerene coupled to tempo, and you can hyperpolarize tempo, and then its cross relaxation path would enhance nuclear spins. So what do you think of that direction for Overhauser DNP?
It's a very promising pathway, I think, because your prospect is much higher, because if you use a triplet state, your saturation factor can be much higher. However, the way is also very long, because little is known about this. But I definitely think it's a way to pursue. So because you can also use a laser, for instance, instead of microwaves.